Welcome to the lecture 2 on renewable energy sources and applications. Myself Dr. Saradindu Panda. The topic will be discussed on introduction to solar energy and working principle of solar cell. The sun does more than for our planet than just provide light during the daytime. Each particle of sunlight, called a photon, that reaches the earth contains energy that fuels our planet. Solar energy is the ultimate source responsible for all of our weather systems and energy sources on earth, and enough solar radiation hits the surface of the planet each hour to theoretically fill our global energy needs for nearly an entire year. Solar is one of the fastest growing and cheapest source of power in the world and will continue to spread rapidly in the coming years. With solar panel technology improving each year, the economic benefits of solar improve, adding to the environmental perks of choosing a clean, renewable energy source. Most of the developed countries are switching over to the solar energy as one of the prime renewable energy source. The current architectural designs make provision for photovoltaic cells and necessary circuitry while making the building plans. What is solar energy? Solar energy is the most abundant energy resource on Earth. Our sun, like any star in the galaxy, is like a massive nuclear reactor. Deep in the sun's core, thermomolecular fission reactions produce massive amounts of energy that radiates outward from the sun's surface and into the space in the form of electromagnetic radiation like visible light, infrared, ultraviolet, X-ray and radio waves and heat. Radiant energy from the sun has powered life on Earth for many millions of years. The spectrum of solar light at the Earth's surface is mostly spread across the visible and near infrared ranges with a small part in ultraviolet region, just like it's shown in the figure below. About the 100% incoming solar energy, the 6% is reflected by the atmosphere, 20% is reflected by the clouds, 4% is reflected from the Earth's surface, and 16% is absorbed by the atmosphere, 9% is absorbed by the clouds, 7% conduction and the rising air, and the 51% is absorbed by the land of the oceans of the earth. From them, the 64% is radiated to the space from the clouds and the atmosphere. 6% is radiated directly to space from the earth. So this is the solar energy distribution. Some energy is absorbed by the earth and some energy is reflected from the earth. So now solar map of India. India is one of the sun's most favored nations, blessed with about 5,000 trillion kilowatt hour per year energy is incident over India's land area, with most parts receiving 4 to 7 kilowatt hour per square meter per day, mainly at the western region of India. Even if a tenth of this potential was utilized, it could mark the end of India's power problems by using the country's deserts and farmland to construct solar plants. Renewable energy has the potential to re-energize India's economy by creating millions of new jobs, allowing the country to achieve energy independence, reduce its trade deficit, and propel it forward as a green nation. Solar energy is the most cost-effective option for India to reduce energy poverty without having to extend the national grid services to provide power for individual homes and the buildings. Solar power can be harnessed and converted to usable energy using photovoltaics or solar thermal collectors. Photovoltaics are much more common for smaller scale electricity projects like residential solar panel installations. Solar thermal capture is typically only used for electricity production on massive scale in utility solar installations. The left side figure is described how the photovoltaic solar system works, and the right side picture gives the some overview of the solar thermal collector system, which I will discuss in next lecture. Photovoltaic comes from the words photo means light and volt a measurement of electricity. Photovoltaic electricity is generated by using the photovoltaic system. The voltage induced by the photovoltaic cell depends on the intensity of light incident on it. The basic photovoltaic system consists of 6 components. That is, most useful component is the solar panel. Next, the charge controller, battery system, inverter, AC/DC switches, and the optional infrastructure is that is AC generators. The solar panel is mainly responsible to collect the solar radiations and transform it into the electrical. Charge controller prevent the overcharging of the batteries. Batteries are responsible to store the power. Inverter is responsible for DC to AC conversion for the AC appliances, and the DC-AC safety switches are responsible for safety purposes. The optional infrastructure is the AC generators to generate the AC. This is the system wiring diagram of the photovoltaic system. The photovoltaic cells are made with a panel, and the panels are connected with the combiner, and it is connected to the charge controller. Charge controller is connected to the battery bank, then it is connected to the power inverter, then it is connected to the AC/DC switches and meters and the AC generators. Now, what is the solar cell? It is a semiconductor device that converts the solar energy directly to the DC electric energy. It supplies a voltage and a current to a resistive load like light, battery, motors, fans, etc. Most of the cell materials are non-productive of greenhouse gases and non-toxic. It is made up with a P-type semiconductors and the N-type semiconductors, making the PN junctions. Anti-reflective coatings are used on it, and finally the upper portion and the lower portion are covered with the metal conductor strips for taking the contact. The efficiency range from a few percent to above 40%. Usage range from the portable electronics just like a calculator or to the spaceships for the power generation. The history of solar cell. In 1839, the French physicist A.E. Becquerel first recognized the photovoltaic effect. After that, in 1883, first solar cell built by Charles Freites coated semiconductor selenium with an extremely thin layer of gold to form the junctions. 1954, Bell Laboratories experimenting with semiconductors. Accidentally, they found that the silicon doped with certain impurities was very sensitive to light. Darrell Chaplin, Kelvin Fuller, and the Gerald Pearson invented the first practical device for converting sunlight into the useful electrical power, resulted in the production of the first practical solar cells with a sunlight energy conversion efficiency of around 6%. Finally, in 1958, first spacecraft to use the solar panels was US satellite Vanguard 1. Now come to the working principle of solar cell. The light incident on the semiconductor material may be passed or reflected through it. The PV cell is made of semiconductor material which is neither a complete conductor nor an insulator. This property of semiconductor material makes it more efficient for converting the light energy into the electric energy. The electrons of the semiconductor material are joined together by the covalent bond. The electromagnetic radiations are made of small energy particles called photons. When the photons in the sunlight are incident on the semiconductor material, its energy is given to an electron in the crystal lattice. Usually, this electron is in the valence band. The energy given to the electron by the photon excites it into the conduction band, where it is free to move around within the semiconductor, causing the electric potential difference. The network of covalent bonds that the electron was previously a part of now has one fewer electron. This is known as a hole. The presence of a missing covalent bond allows the bonded electrons of neighboring atoms to move into the hole, leaving another hole behind, thus propagating holes through the lattice in the p-type material. It can be said that the photons absorbed in the semiconductor create the electron-hole pairs. The energized electron is known as the photoelectrons, and the phenomenon of the emission of electrons is known as the photoelectric effect. The working of the photovoltaic cell depends on the photoelectric effect. Due to the effect of an electric field, the particles move only in the one direction and develops direct current starts to flow through the material in the order to cancel out the potential difference. The semiconductor materials have the metallic electrodes through which the current goes out of it. The most commonly known solar cell is configured as a large area PN junction made from the silicon. As simplification, one can imagine bringing a layer of N-type silicon into the direct contact with layer of P-type silicon. This is the N-type semiconductor. This is the P-type semiconductor. When the N-type and P-type semiconductors are brought together, then there is, due to the diffusions, the depletion region will be produced, and this is the metal contacts at the upper portion, and this is the metal contacts of the lower portion. The photons are incident on the N-type semiconductor materials. So in practice, PN junctions of silicon solar cells are not made in this way, but rather by diffusing an N-type dopant into one side of the P-type wafer or vice versa. In practice, PN junctions of silicon solar cells are not made in this way, but rather by diffusing on N-type dopant into one side of the P-type wafer or vice versa. If a piece of P-type silicon is placed in close contact with a piece of N-type silicon, then diffusion of electrons occur from the region of the higher electron concentration, that is N-type side of the junction, to the P-type, and into the region of the low electron concentration P-type side of the junction. When the electrons diffuse across the PN junction, they recombine with the holes on the P-type side. However, in the absence of an external circuit, this diffusion of carriers does not go on indefinitely because charges build up on either side of the junction and create the electric field. The electric field promotes the charge flow known as the drift current that opposes the eventually balances out the diffusion of the electrons and holes. This region where the electrons and holes have diffused across the junction is called the depletion junction. or the depletion region because it contains the practically no mobile charge carriers. It is also known as the space charge region, although the space charge extends a bit further in both directions than the depletion. Now the charge carrier separation. There are two causes of charge carrier motion and the separation in a solar cell. One is the drift of the carriers, driven by the electric field with electrons being pushed one way and holes the other way. This is the electrons flow and this is the hole flow. Diffusion of carriers from zones of the higher carrier concentration to zones of the lower carrier concentration following a gradient of the chemical potential. These two forces may work one against the other at any given point in the cell. For instance, an electron moving through the junction from the p region to the n region is being pushed by the electric field against the concentration gradient. The same goes for a hole moving in the opposite direction. The current is generated when considering electron hole pairs that are created in the depletion zone. This is the depletion zone, which is where there is a strong electric field. The electron is pushed by this field towards the n side and the holes towards the p side. This is the holes towards the p side, and this is the electrons towards the n side. When the pair is created outside the space charge zone where the electric field is smaller, diffusion also acts to move the carriers, but the junction still plays a role by sweeping any electrons that reach it from the p side to the n side, and by sweeping any holes that reach it from the n side to the p side, thereby creating a concentration gradient outside the space charge zone. In the thick solar cells, there is very little electric field in the active region outside the space charge zone. So, the dominant mode of the charge carrier separation is diffusion. In these cells, the diffusion length of the minority carriers must be large compared to the cell thickness. In the thin film cell, such as the amorphous silicon cell, the diffusion length of the minority carriers is usually very short due to the existence of the defects, and the dominant charge separation is therefore driven by the electrostatic field of the junction, which extends to the whole thickness of the cell. Once the minority carrier enters the drift region, it is swept across the junction, and at the other side of the junction becomes a majority carrier. This reverse current is a generation current fed both thermally and by the absorption of light. On the other hand, the majority carriers are driven into the drift region by diffusion, which leads to the forward current. Only the majority carriers with the highest energies can fully cross the drift region. Therefore, the carrier distribution in the whole device is governed by the dynamic equilibrium between the reverse current and the forward current. When the solar cell is connected to the external load, then the ohmic metal semiconductor contacts are made to both an n-type and p-type sides of the solar cell, and the electrodes connected to an external load. Electrons that are created on the n-type side or created on the p-type side, collected by the junction and swept onto the n-type side, may travel to the wire, power the load, and continue through the wire until they reach the p-type semiconductor metal contact. Here they recombine with a hole that was either created as an electron hole pair on the p-type side of the solar cell, or a hole that was swept across the junction from the n-type side after being created there. The voltage measured is equal to the difference in the quasi-Fermi levels of the majority carriers, that is electrons in the n-type portion and holes in the p-type portion at the two terminals of the solar cell. This is the equivalent circuit of the solar cell. To understand the electric behavior of a solar cell, it is useful to create a model which is electrically equivalent and is based on the discrete ideal electrical components whose behavior is well defined. An ideal solar cell may be modeled by a current source in parallel with a diode. In practice, no solar cell is ideal, so a shunt resistance and a series resistance component are added to the model. This is the shunt resistance, this is the shunt current, this is the diode current, this is the load current. So the total IL, actually the load current, this is the ID, ISH and I. The resulting equivalent circuit and the symbol of the solar cell is shown on the right. This is the equivalent circuit and this is the equivalent symbol of the solar cell which is used in the circuit. These are the reference. We will go through this reference. Thank you.